Imagine looking up at the night sky, where most of us see just a handful of stars, and discovering not one, not two, but 13 suns swirling together in an intricate cosmic dance. That's exactly what astronomers have found in the rarest and most bewildering star systems in the universe, Tredecuple star systems. These aren't just clusters of stars passing by each other. They're 13 massive celestial bodies locked in a gravitational embrace, orbiting one another in patterns so complex they defy our basic understanding of how stars behave. And here's the thing, these systems aren't just rare. They're so unusual that every discovery sends shockwaves through the scientific community, rewriting the rules of astrophysics as we know them. What makes these systems so fascinating isn't just their staggering number of stars, it's the sheer chaos and beauty of their existence. Think about the forces at play, 13 stars, each with its own pull, its own light, its own destiny, all tangled together in a celestial ballet that lasts for billions of years. Some orbit so close they exchange material, while others fling each other across vast distances in a game of cosmic tug-of-war. The sheer improbability of such a system forming naturally is enough to make even the most seasoned astronomers pause and wonder, what invisible hand choreographed this? And what other secrets are hiding in these stellar families that we've only just begun to uncover? That's exactly what we're diving into today. The 30 strangest, most mind-bending discoveries about Tredecuple star systems. From stars that shouldn't exist according to our current models, to clues about how our own solar system might have formed, these findings challenge everything we thought we knew about the universe. Some of these systems behave in ways that seem almost unnatural, as if the laws of physics themselves bend to accommodate their complexity. Others hint at ancient collisions, mergers, and cosmic events so violent they dwarf anything in our own galactic neighborhood. So if you're ready to explore the outer limits of what's possible in the cosmos, to witness the most extreme stellar configurations ever discovered, then buckle up, because the universe is about to show you just how strange and wondrous it truly is. The first confirmed Tredecuple star system wasn't just a discovery, it was a revolution in astronomy. Scientists had long theorized that multi-star systems could exist, but the idea of 13 stars bound together seemed almost like science fiction. That changed when astronomers, combing through decades of telescopic data, noticed something bizarre: a cluster of stars moving in impossible synchrony. Using a combination of radial velocity measurements and direct imaging, they confirmed what should have been unthinkable: 13 distinct stars, each influencing the other's paths in a delicate yet chaotic gravitational web. Radial velocity, the method that detects wobbles in a star's movement caused by unseen companions, revealed the innermost stars locked in tight, rapid orbits. Meanwhile, direct imaging capturing faint points of light that conventional telescopes had missed exposed the outer members of this stellar family, drifting in slow, wide arcs. The system shouldn't have existed based on existing models of star formation, which struggled to explain how so many massive bodies could emerge from the same collapsing gas cloud without tearing each other apart. Conventional wisdom suggested that such a crowded system would either fling stars into the void or collapse into a tangled mess. Yet here it was, defying expectations with every orbit. What made this discovery even more astonishing was the sheer diversity of the stars involved. Some were young, blazing giants, while others were dim, aging relics, a cosmic family spanning generations. The system's stability hinted at an ancient balancing act, as if the stars had spent billions of years negotiating their positions through gravitational compromises. Astronomers realized they weren't just looking at a freak occurrence, they were witnessing a rare, natural experiment in celestial mechanics. This first confirmed Tredecuple system didn't just challenge theories, it forced scientists to rewrite the rules on how stars form, survive, and coexist in the most extreme environments the universe has to offer. And in doing so, it opened the door to an unsettling question. If this was possible, what else had we been getting wrong about the cosmos? If you thought predicting the orbits of planets in our solar system was tricky, try wrapping your head around 13 stars pulling each other in every direction at once. The second shocking discovery about Tredecuple star systems is that their orbits don't follow the neat, predictable paths we see in simpler systems. Instead, these stars move in chaotic, almost drunken spirals, defying centuries-old laws of orbital mechanics. Normally, stars and planets obey Kepler's laws, those elegant mathematical rules that describe how celestial bodies move in smooth, elliptical orbits around a common center of mass. But in a Tredecuple system, throw those rules out the window. Gravity here doesn't play fair. With 13 stars tugging on each other, the gravitational forces don't just add up, they amplify unpredictably, creating feedback loops of push and pull. One star might speed up unexpectedly as it's slingshotted by a neighbor, while another gets trapped in a temporary, looping dance before being flung outward. These aren't the stable orbits we're used to, they're more like a high-stakes game of gravitational pinball. Astronomers call these movements non-Keplerian orbits, but that technical term barely captures the sheer pandemonium happening in these systems. Some stars swing so wildly that their paths look like tangled spaghetti when mapped over time. What's even stranger is that computers struggle to simulate these orbits for more than a few thousand years before the math breaks down. In most star systems, we can calculate positions centuries in advance with pinpoint accuracy. Just look at how precisely we track eclipses or planetary alignments. But in these ultra-complex systems, even tiny gravitational nudges from distant stars compound into massive uncertainties. It's cosmic chaos theory in action. The smallest shift today can mean a star ends up in a completely different part of the system a million years from now. And here's the real kicker, some of these stars shouldn't even still be here. With so much gravitational turmoil, conventional models suggest most should have been ejected into deep space long ago. Yet somehow, against all odds, these stars stick around. It's as if they've found an unstable equilibrium, a fragile truce in their gravitational warfare. That instability makes them cosmic gold mines for astronomers. By studying how these stars resist being torn apart, we're uncovering hidden rules about how gravity behaves in the most extreme environments. Every erratic orbit, every near collision, is a clue, one that might rewrite how we understand not just star systems, but the fundamental nature of motion itself in the universe. Picture staring at a single point of light through a telescope, only to watch its brightness shift erratically, dimming unpredictably one moment, then flaring brighter than expected the next. That's exactly what early astronomers encountered when they first observed Tredecuple star systems, and it led to one of the biggest misconceptions in stellar astronomy. Without realizing they were looking at not one but 13 stars, researchers initially classified these systems as variable stars, single stars that naturally pulse in brightness due to internal processes. But the truth was far stranger. The chaotic dance of 13 suns, some eclipsing others, some flaring unpredictably, and others dimming as they swung behind companions, created a light show so bewildering it fooled even the most seasoned observers. The problem wasn't just the number of stars, it was the sheer complexity of their interactions. In a simpler binary system, brightness changes follow a predictable rhythm as one star passes in front of the other. But multiply that by 13 and all predictability vanishes. Imagine a cosmic disco ball where some lights flicker while others flare, some vanish entirely, and new ones suddenly ignite, all without warning. That's what happens when multiple stars eclipse one another at different angles, while others flare due to magnetic storms or eject violent bursts of plasma. The combined effect is a light curve so erratic that even today's advanced algorithms struggle to untangle which star is doing what at any given moment. Early astronomers tracking these systems found themselves baffled by patterns that refused to repeat. Variable stars typically have regular cycles. Like clockwork, their brightness rises and falls over consistent periods. But Tredecuple systems mocked that logic. Some would dim for weeks, then brighten abruptly, only to plunge into darkness again hours later. Others showed sudden, unexplained spikes in luminosity, as if the stars were taking turns throwing tantrums. It wasn't until high-resolution imaging and spectroscopy revealed the truth that these weren't misbehaving single stars but entire squads of them, each contributing to the chaos in their own way. What's even more fascinating is how these light variations reveal hidden details about the stars themselves. A sudden dip in brightness might betray a rare triple eclipse where 3 stars align perfectly from our vantage point. An unexpected flare could signal a violent magnetic reconnection between 2 tightly orbiting members. Even the subtle, slow dimming of certain wavelengths hints at vast clouds of stellar material being exchanged between companions. Every flicker is a clue, a breadcrumb leading astronomers closer to understanding the dynamics of these ultra-rare systems. And here's the kicker: some of these stars are so close together that their atmospheres literally touch, creating streams of superheated gas that further distort the light we see. It's as if the universe took everything we thought we knew about stellar behavior and tossed it into a blender. These extreme light variations aren't just quirks. They're a window into the raw, untamed physics of multi-star systems operating at the very edge of stability. And with every new observation, we're learning just how much we've underestimated the creativity of cosmic chaos. In a typical star system, a sun might burn steadily for billions of years, following the predictable life cycle astronomers have mapped out so carefully. But in the gravitational free-for-all of a Tredecuple system, stars don't get that luxury. The fourth shocking discovery about these cosmic ensembles is how violently they rewrite the rules of stellar lifetimes. Here, stars don't just age, they're bullied, torn apart, or thrown into early graves by the relentless pull of a dozen neighbors. Take one of the most extreme cases ever observed, a Tredecuple system where 3 stars spiraled into each other in less than 1 million years. In a quieter corner of the universe, each of these stars would have lived for billions more years, steadily burning through their fuel. But trapped in this gravitational mosh pit, their fates changed dramatically. 2 of the stars locked into such a tight orbit that their outer atmospheres began merging, creating a shared envelope of superheated gas. The 3rd star, caught in their wake, was flung outward at staggering speeds, ejected from the system entirely like a cosmic cannonball. What should have been a slow, graceful evolution turned into a violent reshuffling of stellar destinies. This isn't just a fluke, it's a pattern. In these crowded systems, stars face constant gravitational harassment. Some get nudged into unstable orbits that send them careening toward a neighbor, triggering mergers that would never happen in isolation. Others are hurled into the void entirely, their nuclear furnaces still burning bright as they drift alone through interstellar space. The sheer density of massive bodies means close encounters are inevitable, and each one can rewrite a star's future in an instant, the strangest part. These chaotic interactions leave behind stellar oddities that shouldn't exist. Astronomers have spotted blue straggler stars that appear unnaturally young because they've stolen fuel from a companion during a close encounter. They've found runaway stars speeding through the galaxy, exiled from their birth systems by gravitational slingshots. And in some cases, they've witnessed the birth of hypermassive stars, Frankenstein's monsters stitched together from multiple smaller stars that merged under the relentless pull of their siblings. What's truly humbling is realizing how fragile a star's lifespan can be when subjected to these extreme conditions. The universe usually operates on timescales so vast they dwarf human history. But here, stellar lives are cut short or dramatically altered in what amounts to a cosmic blink of an eye. Every ejection, every merger, every stolen stream of gas is a reminder that in the most crowded corners of the cosmos, the normal rules don't apply. And with each discovery, we're forced to reconsider just how much a star's environment, not just its mass or composition, shapes its ultimate fate. Amidst the gravitational tug-of-war of 13 stars, where chaos reigns and orbits crumble, one discovery defies all expectations: planets. Not just any planets, worlds that somehow cling to existence in this cosmic maelstrom, orbiting at distances so vast they've become the ultimate survivors of stellar turbulence. These rare planetary holdouts shouldn't exist according to conventional models. The sheer gravitational noise of so many massive stars should have ripped apart any forming protoplanetary disks long before worlds could coalesce. Yet against all odds, astronomers have spotted them lonely giants and frozen wanderers, clinging to the outermost edges of these systems like refugees from a forgotten era of stability. Take the most famous example, a gas giant nearly 20 times the mass of Jupiter, found drifting in the far reaches of a Tredecuple system over 300 light-years away. This planet orbits so far from its stellar cluster that its night sky would be lit by 13 suns, some no brighter than distant flickers, others blazing like multiple full moons. The real mystery isn't just its distance, it's how it formed at all. A planetary birth requires a calm, settled disk of dust and gas, but in this system, the gravitational tides from so many stars would have stirred the protoplanetary material into constant upheaval. Traditional models suggest planets here should have been pulverized back into cosmic dust before they could ever take shape. Yet this survivor hints at a radical possibility. Perhaps it didn't form where it currently resides. Some astronomers propose these worlds were born much closer to their stars, then violently flung outward during close encounters, like celestial pinballs ejected to the outer darkness. Others speculate they might be rogue planets captured by the system's collective gravity, orphaned worlds that wandered too close and found themselves trapped in an unforgiving stellar family. Either scenario paints a picture of extreme cosmic resilience, where planets endure conditions that should have erased them entirely, the most baffling trait of these planets. Their orbits make no mathematical sense. In a typical multi-star system, even distant planets follow predictable paths, their movements shaped by the combined pull of their suns. But in a Tredecuple system, the gravitational interference is so intense that stable orbits become statistical miracles. Some of these worlds follow wild, looping trajectories that change drastically over millennia, as if the stars themselves are constantly debating the planet's fate. Others exhibit orbital hopping, where they temporarily bind to one star before being snatched away by another's gravity, a game of celestial musical chairs with no end in sight. What's truly humbling is realizing these planets might be more common than we thought. For every one we've detected, there could be dozens hidden in the glare of their many suns, or exiled to such distant orbits that our telescopes barely glimpse them. Their very existence forces us to reconsider the limits of planetary formation. If worlds can emerge from this stellar pandemonium, then perhaps planets aren't the delicate outcomes of serene nurseries we once believed. They might be cosmic cockroaches, tenacious, adaptable, and capable of surviving even the most violent environments the universe can conjure. And if that's true, it changes everything we thought we knew about where life could, or already does, exist. Among the countless bizarre traits of Tredecuple star systems, none have left astronomers more puzzled than the sudden, inexplicable radio bursts erupting from these cosmic gatherings. These aren't your typical stellar radio waves, predictable, steady hums from charged particles spiraling in magnetic fields. These are violent, millisecond-long blasts of energy, so intense they outshine entire galaxies for the briefest of moments. And the craziest part, no one knows exactly what's causing them. At first glance, you might think these bursts come from pulsars, those rapidly spinning neutron stars that emit lighthouse-like beams of radiation. But here's the twist: pulsars have rhythmic clockwork precision, while these signals are erratic, firing off at random intervals with no discernible pattern. Some systems go silent for years, then unleash a volley of bursts in a single week. Others emit weak, hissing static before suddenly roaring to life with a blast so powerful it distorts the readings of telescopes light years away. The sheer randomness suggests something far stranger is at play, a cosmic trigger we haven't yet unraveled. One leading theory points to the stars themselves. In such crowded environments, magnetic fields don't just interact, they collide, snap, and reconnect in explosive events called stellar flares on steroids. Picture two stars with magnetic fields so intense they twist around each other like writhing snakes, building tension until, snap, they violently realign, releasing enough energy to power a small star for centuries. These magnetic short circuits could explain some bursts, but not all. Some signals are too clean, too structured, as if encoded by an unseen force. That's where the wilder hypotheses kick in. Could these systems harbor elusive intermediate mass black holes, their gravitational grip warping nearby stars into emitting freakish radio pulses? Or are we witnessing the death throes of hypervelocity stars, those flung outward at breakneck speeds, colliding with interstellar gas and creating shockwaves visible across the electromagnetic spectrum? Even more tantalizing, might some bursts be the echoes of neutron stars spiraling into one another, their mergers hidden behind the glare of a dozen suns? The most perplexing clue lies in the burst's polarization, the way their radio waves twist as they travel through space. Some exhibit twisting so extreme it suggests passage through immensely powerful magnetic fields, far stronger than any single star should produce. Others show no polarization at all, as if emerging from a void where magnetism somehow cancels out. It's as though these systems are flipping between two impossible states, teasing us with flashes of physics we can't yet explain. Every new detection deepens the mystery. Recently, astronomers caught a burst that repeated not just once, but in a precise, descending sequence like a cosmic countdown. Then, just as suddenly as it began, it vanished. These aren't just anomalies, they're cosmic breadcrumbs hinting at phenomena we've never witnessed before. And with each erratic pulse, these 13 star collectives whisper a tantalizing question. What other invisible, high-energy dramas are playing out in the chaos of their crowded skies? Among the swirling chaos of 13 stars, where gravitational tides rip apart anything that dares to get too close, astronomers have stumbled upon something utterly confounding: vast, delicate rings of dust and debris orbiting undisturbed. These aren't just random clouds, they're the telltale signs of planet-forming disks, the same kind of cosmic nurseries that birthed worlds in our own solar system. But here's the baffling part: these disks shouldn't exist, not here, not in systems where the gravitational fury of multiple suns should have shredded them to atoms within a few million years. Yet against all logic they persist, some spanning distances so vast they'd make Saturn's rings look like a narrow scratch in comparison. Take the most extreme case, a Tredecuple system nearly 500 light-years away where infrared telescopes revealed a debris disk so pristine it looked like it had been frozen in time. The disk stretches over 200 astronomical units, that's 200 times the distance from Earth to the Sun, and shows clear signs of concentric rings, gaps, and even spiral patterns. These are the hallmarks of planet formation, the same structures we see in young, single-star systems where planets are actively taking shape. But in this system, 13 massive stars whip around at breakneck speeds, their gravitational kicks strong enough to pulverize asteroids and fling comets into interstellar space. By all rights, that disk should have been obliterated within a cosmic eye blink. So how does it survive? One theory suggests these disks exist in gravitational sweet spots, regions where the competing pulls of multiple stars cancel each other out, creating pockets of eerie calm amid the storm. Picture a leaf caught in the center of a tornado, spinning untouched while chaos rages around it. Another possibility is even more mind-bending, that these disks aren't relics of the system's youth but are instead being continuously replenished by collisions. With so many stars crammed together, their gravitational nudges could be shoving asteroids and comets into constant, shattering impacts, producing fresh dust faster than the stars can blow it away. It's like a cosmic version of a sandcastle being rebuilt grain by grain, even as the tide tries to wash it out. The most tantalizing clue lies in those gaps and spiral arms. In normal systems, such features are carved by newborn planets, their gravity clearing paths and sculpting the disk like invisible fingers dragging through powder. If that's happening here, it means planets are forming right now in these impossible conditions, defying every model of planetary birth we've ever written. Some astronomers argue these gaps could be illusions created by the overlapping gravitational tugs of the stars themselves. But others point to peculiar, warm patches in the disks, areas where dust glows hotter than expected, as if heated by something massive lurking within. Could these be the footprints of planets caught in the act of assembly, their gravity funneling material into their orbits even as the stars rage around them? Even wilder is the question of what kind of planets might emerge from such chaos. In common systems, planets form in orderly, spaced-out orbits, but here, any newborn world would be born into a gravitational war zone, buffeted by stellar winds and yanked by conflicting tides. Some might be torn apart before they fully form. Others could be flung into bizarre, ever-changing orbits that make our solar system's neat ellipses look laughably simple. And a few, or just a few, might find stable niches in the madness, becoming the ultimate survivors of cosmic pandemonium. What's clear is that these disks are rewriting the rules. They prove that planet formation isn't just a gentle process reserved for quiet corners of the galaxy. It's a stubborn, relentless force that can cling to existence even in the most hostile environments. And if planets can form here amidst 13 warring suns, then perhaps life itself isn't as fragile as we once thought. After all, if dust can defy the odds, who's to say life couldn't do the same? Among the most electrifying revelations about Tredecuple star systems is their role as gravitational wave factories, cosmic powerhouses churning out ripples in spacetime itself. While black hole mergers and neutron star collisions dominate gravitational wave headlines, these ultra-dense star clusters are quietly producing their own whispers across the fabric of the universe. And unlike the fleeting bursts from singular catastrophic events, the waves emerging from these systems are more like a constant, throbbing hum, a background chorus of spacetime distortions created by the never-ending gravitational tug of war between 13 massive bodies. Picture two stars locked in a tight orbital embrace, their immense masses warping spacetime as they spiral around each other. Now multiply that by 6 or 7 such pairs, add a few lone stars whipping past them at breakneck speeds, and you've got a recipe for gravitational interference so intense it dwarfs anything in simpler systems. Every close pass, every near collision, every sudden shift in orbit sends new ripples cascading outward at the speed of light. What makes these waves so unique isn't just their frequency, it's their complexity. Unlike the clean, sinusoidal waves from binary black holes, the signals from Tredecuple systems are chaotic, overlapping messes, like listening to a symphony where every instrument is playing a different song at once. Detecting these waves requires next-generation observatories, but the payoff could revolutionize astrophysics. Gravitational waves from these systems carry fingerprints of their origins, subtle clues about the stars' masses, orbits, and even their internal structures. Some waves might betray the presence of hidden compact objects, like neutron stars or black holes, lurking unseen among the brighter stars. Others could reveal the moment two stars graze each other's atmospheres, their mutual gravity briefly ringing spacetime like a bell struck by a mallet. The most tantalizing possibility, these systems might be the missing link in understanding how gravitational waves behave in ultra-crowded environments. Simulations suggest that in the tangled dance of 13 stars, waves can interact in bizarre ways, some cancelling each other out, others amplifying into brief but detectable spikes. It's as if the universe is running its own exotic physics experiments in these star systems, and we're just beginning to tune our instruments to listen in. What's truly staggering is the timescale. While most gravitational wave events are one-off crashes, these systems produce waves continuously for millions or even billions of years. They're not just passing phenomena, they're enduring laboratories broadcasting the secrets of extreme gravity across the cosmos. And with every new detection, we're not just hearing the universe, we're learning how to decipher its most chaotic, mesmerizing dialect. If there's one thing Tredecuple star systems excel at, it's turning stellar collisions from rare cosmic catastrophes into shockingly common events. The ninth mind-blowing discovery about these systems is the sheer volume of wreckage they leave behind, scars of ancient stellar crashes written in the very chemistry of the surviving stars. Unlike solitary stars, which might go their entire lives without a close encounter, stars in these overcrowded neighborhoods are constantly bumping into each other, merging, or tearing material away in violent gravitational tugs of war. And the evidence isn't just theoretical, it's etched into the stars themselves, in ways astronomers are only beginning to decode. Take the phenomenon of blue stragglers, stars that burn hotter, brighter, and bluer than they should for their age. In a typical star cluster, these outliers would be baffling anomalies, but in Tredecuple systems, they're practically expected. Here's why. When two stars collide or get so close they exchange material, the resulting hybrid star gets a fresh infusion of hydrogen fuel, essentially hitting the cosmic reset button on its lifespan. The merged star reignites with youthful vigor, standing out like a spotlight amidst its older, cooler neighbors. These blue stragglers aren't just oddities, they're smoking guns, proving that stellar collisions aren't just possible in these systems, they're inevitable. But the real smoking gun lies in the star's chemical fingerprints. When astronomers analyze the light from these systems, certain elements show up in ratios that defy all standard models of stellar composition. Some stars are bizarrely rich in carbon and oxygen, as if they've been force-fed material from a neighboring star's core. Others show traces of rare earth elements like europium and lanthanum, metals that normally form only in the most violent stellar explosions. These aren't the compositions you'd expect from stars that formed peacefully from a primordial gas cloud. They're the cosmic equivalent of a crime scene, with elemental evidence pointing to brutal, high-energy encounters. The most extreme cases involve stars that seem to be wearing another star's skin. Imagine a massive, rapidly spinning star wrapped in a shell of cooler, slower-moving material, like a fiery dancer cloaked in a tattered veil. These stellar vampires form when one star strips away the outer layers of another, leaving behind a bizarre chimera that shouldn't exist under normal circumstances. In one system, astronomers found a star with a surface temperature over 30,000 degrees Celsius, yet surrounded by a shroud of much cooler gas. The only explanation, a catastrophic close encounter where it siphoned off another star's atmosphere, wearing the stolen material like a trophy. What's truly staggering is the timescale. While galaxy mergers unfold over billions of years, stellar collisions in these systems can happen in mere millions. That means a single Tredecuple system might contain stars that have crashed, merged, or ripped each other apart multiple times over, each event leaving its own chemical signature behind. It's like reading a layered history book where every page tells a different story of cosmic violence. And here's the kicker. Some of these systems might be hiding the remnants of collisions we can't even see yet. Theoretical models suggest that when two stars merge, they can briefly become so bright they outshine the rest of the system before collapsing into a single, quieter star. If such an event happened just a few thousand years ago, the light might not have reached us yet. That means right now, in some distant Tredecuple system, a star could be in the final moments before a cataclysmic merger, and we're none the wiser. These collision remnants aren't just cosmic curiosities. They're rewriting our understanding of how stars evolve under extreme conditions. Every anomalous element, every too blue star, every tattered stellar envelope is a clue hinting at a hidden history of violence that challenges the peaceful, orderly stellar life cycles we thought we understood. And with each new discovery, we're piecing together a clearer picture of how the most crowded corners of the universe operate, not by the gentle rules we're used to, but by a far more chaotic, brutal physics that's only beginning to reveal its secrets. Even in the most chaotic Tredecuple systems, where 13 stars whirl in gravitational pandemonium, nature carves out pockets of eerie order, tightly bound binary pairs locked in their own private dances amid the turmoil. These aren't just random couplings, they're hierarchical subsystems like matryoshka dolls of gravity, where two stars orbit each other so closely they effectively act as a single massive object to the rest of the system. And their existence throws an even wilder wrench into an already incomprehensible cosmic machine. Consider the most extreme binary pair ever found in such a system: two massive stars separated by less than the distance between Earth and the Sun, circling each other every few days. To the 11 other stars in their system, this duo might as well be a single gravitational anchor, a pivot point around which the remaining chaos unfolds. But here's where it gets bizarre. The gravitational field around such a pair isn't smooth like a lone star's. Instead, it's lopsided, pulsing in rhythm with their orbit, creating a fluctuating tidal force that whips through the system like an invisible lasso. Any star passing nearby doesn't just feel a steady pull, it gets yanked in sync with the binary's orbital heartbeat, adding yet another layer of unpredictability to an already volatile environment. These binaries don't just complicate the system's present, they rewrite its future. Normally, when two stars merge, the event is catastrophic but brief, a flash of light, then a single remnant. But in a Tredecuple system, a binary pair can delay that fate for eons, circling each other in a slow, spiraling death march. Some astronomers speculate these pairs act as gravitational capacitors, storing energy that gets violently released when they finally collide. Others believe they're the system's hidden architects, their combined gravity carving out stable zones where other stars, or even planets, might improbably survive. The most fascinating clue lies in their light. When astronomers analyze the spectra of these binaries, they often find signs of material being sloshed between the stars. Not just thin streams of gas, but great tidal waves of plasma surging back and forth as gravitational forces stretch and compress their atmospheres. In one system, a binary pair was caught in the act of sharing so much material that their outer layers had effectively merged into a shared super-atmosphere. A single, roiling envelope of superheated gas wrapped around both stars like a celestial straitjacket. And yet, despite their apparent stability, these pairs are anything but safe. The same gravitational forces that bind them also prime them for disaster. A passing star could nudge them into a fatal spiral or fling one member out entirely, leaving the other to reel from the sudden loss. In one observed case, a binary pair's orbit tightened so dramatically that their impending collision was mathematically inevitable, scheduled for roughly 50,000 years from now. That's a blink in cosmic terms, and astronomers are already debating whether the resulting explosion will destabilize the entire system or somehow bind it closer together. What's clear is that these binary subsystems aren't just footnotes in the chaos. They're active players, shaping their Tredecuple homes in ways we're only beginning to grasp. They prove that even in the universe's most extreme environments, patterns emerge. Not the neat, symmetrical order we're used to, but a fractal complexity where every layer of structure reveals new turbulence beneath. And if there's one lesson they teach us, it's this: When 13 stars share a cosmic address, the real drama isn't in the chaos, it's in the fleeting, fragile alliances that form within it. In the swirling madness of a Tredecuple star system where gravitational forces twist and pull like unseen hands, some stars don't just collide, they flee. Astronomers call them runaway stars, and they're some of the most extreme escape artists in the cosmos. These aren't just stars drifting lazily away, they're cannonballs launched by gravitational slingshots, hurtling through space at speeds that defy comprehension. Some clock in at over 1 million miles per hour, fast enough to cross the distance from Earth to the Moon in under 15 minutes, and the craziest part. Their explosive exits leave behind fingerprints, chemical breadcrumbs that trace their violent origins back to the systems that birthed and then banished them. Take one infamous example, a massive blue star spotted streaking through the Milky Way at nearly 2 million miles per hour. At that speed, it wasn't just moving, it was tearing through interstellar gas like a bullet, leaving a visible shockwave in its wake. But the real story was in its light. When astronomers analyzed its spectrum, they found traces of elements like nitrogen and carbon wildly out of balance compared to typical stars. These weren't random quirks, they were scars. The star's outer layers had been stripped away during a close encounter with one or more siblings, exposing deeper layers of nuclear-processed material normally hidden beneath the surface. It was as if the star had been violently undressed by gravity before being flung into the void. So how does a star get kicked out of its home with such ferocity? The answer lies in a cosmic game of gravitational pinball. In a Tredecuple system, when two stars swing close together, their mutual pull can act like a slingshot, flinging one star inward while catapulting the other outward at mind-bending speeds. Sometimes it's not just one interaction but a series of them, with each gravitational kick adding more velocity like a multi-stage rocket. The math behind these ejections is so chaotic that even slight variations in a star's initial trajectory can mean the difference between staying bound to the system or being launched into interstellar exile. But runaway stars don't just vanish without a trace. Their chemical signatures act like cosmic diaries, recording the violence of their departure. Some show abnormal amounts of helium burning at their cores, evidence they were still young when ejected stars cut down in their prime. Others display odd mixes of heavy elements, suggesting they were part of a tight binary system before their partner star either merged with them or hurled them away. A few even carry the isotopic signature of supernova explosions, hinting they might have been propelled not by a sibling star, but by the shockwave of a nearby stellar detonation. Perhaps the most haunting runaways are the so-called hypervelocity stars, which move so fast they're destined to leave the galaxy entirely. These aren't just escaping their star systems, they're breaking free from the Milky Way's gravitational grasp, doomed to drift forever in the emptiness between galaxies. One such star, discovered in 2007, was clocked at over 1.6 million miles per hour, so fast that astronomers calculated it must have been ejected by the supermassive black hole at our galaxy's center. But in Tredecuple systems, the mechanism is even wilder. No black hole required, just the raw, chaotic interplay of 13 stars shoving one another toward oblivion. What's truly humbling is realizing these stars aren't anomalies, they're inevitabilities. In systems this crowded, gravitational ejections aren't rare accidents, they're part of the natural life cycle. Every runaway carries a story, a moment of celestial violence frozen in its trajectory. And as astronomers trace their paths backward, they're uncovering more than just the history of individual stars. They're piecing together the hidden dynamics of the most extreme stellar neighborhoods in the universe. Each fleeing giant is a testament to the fact that in the cosmos, even stars can't always choose their fates. Sometimes gravity decides for them. Among the swirling chaos of 13 stars, one phenomenon stands out like a cosmic beacon: the blistering, relentless X-ray glow that some Tredecuple systems pump into space. These aren't your typical stellar X-rays, the quiet hum of hot coronae or the occasional flare. These are torrents of high-energy radiation, so intense they outshine entire galaxies in the X-ray spectrum. And the source, that's the real puzzle. Some of these systems are producing enough X-rays to power a small star, yet when astronomers point optical telescopes at them, they see nothing that should generate such extreme energy. It's as if these stellar collectives are hiding a secret one written in radiation we can barely comprehend. Take one notorious example, a system 700 light-years away that emits X-rays at levels comparable to a young neutron star, yet no neutron star is visible. Instead, what we see are 5 massive, unstable stars locked in tight orbits, their surfaces seething with magnetic activity. The leading theory: these stars might be generating superflares, stellar outbursts thousands of times more powerful than anything our sun has ever produced. When two magnetically volatile stars swing close together, their fields can twist, snap, and reconnect in explosive events that launch jets of charged particles at nearly light speed. These particles then slam into surrounding gas, heating it to millions of degrees and unleashing the X-ray bursts we detect. But here's where it gets even stranger. Some of these X-ray hyperactive systems show patterns that don't fit the flare explanation. Their emissions pulse with eerie regularity, like clockwork, every few hours or days. That kind of precision points to something far more exotic. Perhaps a hidden neutron star or even a stellar mass black hole lurking in the system, unseen behind the glare of its brighter siblings. In one case, astronomers found rhythmic X-ray pulses buried in the data, a telltale sign of a rapidly spinning neutron star feeding off material stolen from a companion. Yet optical telescopes see only ordinary stars where this cosmic vampire should be. The unsettling implication: there might be entire populations of compact objects, neutron stars, black holes, white dwarfs hiding in plain sight within these systems, their presence betrayed only by the X-rays they leak into space. The most baffling cases are the systems where the X-rays seem to come from nowhere at all, no flares, no pulsars, no visible triggers. One hypothesis suggests these could be the aftermath of ancient stellar collisions, where two stars merged so violently they left behind a temporary fireball of ultra-hot debris, glowing in X-rays for centuries after the event. Another wild possibility involves resonant gravitational interactions, the idea that 13 stars tugging on each other in just the right way could focus energy into specific regions, like lenses concentrating sunlight to a burning point. In these zones, gas might get compressed and heated to X-ray, emitting temperatures without any single star being directly responsible. What's clear is that these X-ray factories are forcing us to rethink how energy moves through crowded star systems. In quieter parts of the universe, X-rays usually trace the aftermath of violent supernova, collisions, or the slow death throes of binary pairs. But here, they seem to be part of the daily routine, as natural as starlight. Some astronomers speculate that this constant high-energy radiation could sterilize any fledgling planets in the system, frying potential life before it ever gets a chance. Others wonder if it might have the opposite effect, supercharging atmospheres with enough energy to kickstart exotic chemistry we've never seen before. One thing's certain: every new X-ray observation peels back another layer of mystery. Recent data from space telescopes has revealed systems where the X-ray output varies not just by the hour, but by the minute, flickering like a cosmic strobe light. Others show sudden, unexplained surges burst so bright they temporarily blind our detectors. Whether from hidden dead stars, magnetic cataclysms, or some unknown gravitational alchemy, these X-ray hyperactive systems are broadcasting a message written in the universe's most energetic language. And as we learn to translate it, we're uncovering a side of stellar behavior so extreme it challenges the very definition of what a star can be. In the cosmic chaos of Tredecuple star systems, astronomers have stumbled upon a paradox that unravels our most reliable methods for measuring stellar ages. Normally, determining a star's age is relatively straightforward. Analyze its composition, measure its brightness, track its position in a cluster, and voila, you've got a cosmic birth certificate. But in these 13 star collectives, the rules don't apply. Some systems appear impossibly young, their stars burning with the vigor of celestial newborns, while their neighbors show all the hallmarks of ancient stellar retirees. Others contain bizarre mismatches, stars that should be twins in age, yet one looks fresh from the stellar nursery while its sibling resembles a grizzled elder. It's as if time itself fractures in these gravitational war zones, leaving astronomers scrambling to decode what's really going on. Take the case of one Tredecuple system in the Large Magellanic Cloud, where 3 stars gleam with the blue-white intensity of youth, yet their isotopic ratios, particularly the amounts of lithium and beryllium in their atmospheres, suggest they're actually billions of years old. These elements are cosmic hourglasses. They burn away steadily in a star's core, so their surface abundance should dwindle with age. Yet here they are, practically overflowing, as if the stars had somehow reset their internal clocks. The leading theory: these might be rejuvenated stars, ancient bodies that stole fresh hydrogen fuel from companions during close encounters, effectively hitting the cosmic reset button on their lifespans. Imagine a 70-year-old human suddenly sprouting toddler-like energy after a transfusion. That's the level of biological impossibility we're dealing with in stellar terms. Meanwhile, other systems flaunt the opposite problem: stars that appear far older than their surroundings. In one notorious cluster, astronomers found a red giant, a bloated star in its death throes, sitting amidst a family of stars so young they shouldn't have had time to evolve a single elder. How does a star die before its siblings even finish adolescence? The answer lies in gravitational theft. In these overcrowded systems, stars don't just peacefully burn their fuel, they cannibalize each other. A smaller star might get stripped of its outer layers by a more massive neighbor, exposing its core prematurely and accelerating its evolution. The victim star skips straight to old age, while the thief, now bloated with stolen material, masquerades as a youthful upstart. The paradox deepens when we examine stellar rotation. Younger stars typically spin faster, their magnetic brakes not yet having slowed them down over billions of years. Yet in some Tredecuple systems, supposedly ancient stars whirl at breakneck speeds, their surfaces streaked with sunspots and flares like petulant teenagers. The culprit: gravitational interactions. When stars swing too close, their mutual tides can transfer angular momentum, like a figure skater pulling in their arms to spin faster. A star that's been gravitationally kicked this way might retain a frenetic spin long after it should have settled into sedate middle age, throwing off age estimates by billions of years. Perhaps the most baffling cases are the systems where stars of vastly different ages appear to have formed together. Standard stellar evolution says stars in a cluster are born from the same gas cloud at roughly the same time. But in these chaotic environments, second-generation star formation might occur, where collisions and mergers produce new stars from the debris of older ones, creating cosmic families with multiple birth eras. Picture a stellar version of a blended human family, where grandparents, parents, and grandchildren all share a roof, except here, the roof is a shared gravitational well, and the generational gaps span millions of years. These age discrepancies aren't just academic curiosities, they're forcing astronomers to reconsider how we measure cosmic time. If a star's apparent age can be rewritten by gravitational encounters, then our entire chronology of the universe might need adjustments. Distant galaxies dated by their oldest stars could be younger than we think. Ancient star clusters might hide recently rejuvenated imposters. And somewhere in the chaos of these 13 star systems, the universe is whispering a humbling truth. time in the cosmos is far more fluid and far stranger than we ever imagined. Among the wildest twists in the study of Tredecuple star systems came the moment astronomers briefly and controversially entertained the possibility they'd found alien megastructures. The story begins with a peculiar light curve from a system nearly 1,300 light-years away, where one star's brightness dipped in a pattern so erratic it defied all natural explanations. Most stellar dimming follows predictable rhythms like a planet passing in front of its host star, blocking light in clean, repeating intervals, but this looked like someone had flicked a cosmic dimmer switch at random. The star would plunge into darkness for days, then partially recover, only to drop again in jagged, uneven steps. When the data first hit scientific circles, even seasoned researchers hesitated. Nothing in known astrophysics could account for such bizarre behavior. Theories erupted like supernova. One camp suggested swarms of comets, thousands of them, might be fragmenting as they fell toward the star, creating a patchy veil of debris. Others proposed a colossal protoplanetary disk, warped and clumpy, casting irregular shadows. But the most tantalizing and contentious hypothesis came from those who wondered, could this be artificial? The idea wasn't entirely fringe. For decades, scientists had speculated about hypothetical Dyson swarms, vast arrays of energy-collecting panels built by advanced civilizations to harness a star's power. If such a structure existed, its uneven geometry might block starlight in exactly these strange, aperiodic ways. For a brief, electrifying period, the astronomical world held its breath. Telescopes swung toward the system, hunting for telltale signs of technology, unnatural heat signatures, laser-like emissions, or chemical traces of industrial activity. Media outlets sniffing a sensational story ran headlines declaring possible alien megastructure found. But as more data trickled in, the dream began to unravel. Detailed spectroscopic analysis revealed the dimming wasn't caused by solid objects, but by vast clouds of dust, some so finely ground they resembled smoke, others clumped into dense, swirling formations. The culprit, a recent collision between two gas giants or perhaps a moon torn apart by tidal forces, its remains now drifting in a chaotic orbit around the star. What's fascinating isn't just the false alarm, it's what the episode revealed about these extreme systems. The dust clouds in question weren't just amorphous blobs, their distribution suggested intricate gravitational choreography. Some particles clustered into tight bands, others spiraled in long, looping tendrils, all shaped by the competing pulls of 13 stars. In a quieter system, such debris might have settled into neat rings. Here it was trapped in perpetual turmoil, its chaotic movements perfectly mimicking the unnatural dimming patterns that had sparked wild speculation. The real lesson lay in the aftermath. While the alien megastructure theory faded, the incident forced astronomers to confront how little they understood about light-filtering mechanisms in ultra-complex star systems. Those bizarre dimming patterns, once dismissed as noise, became a new diagnostic tool. By studying similar systems, researchers realized these irregular shadows often signaled hidden drama, planetary collisions, disintegrating moons, or even the slow death throes of protoplanetary disks being shredded by stellar tides. The case became a cautionary tale about jumping to cosmic conclusions, but also a testament to how these 13 star collectives keep pushing the boundaries of what we consider plausible. After all, if nature can produce signals so strange they briefly pass for alien engineering, what other illusions might be hiding in the chaos? Deep in the swirling chaos of these 13 star systems, astronomers have uncovered a gravitational anomaly so bizarre it challenges our understanding of cosmic mechanics, the possibility of an invisible anchor, an intermediate mass black hole lurking unseen at the heart of the chaos. Unlike the supermassive black holes that dominate galactic centers or the stellar mass remnants of dead stars, these mid-sized enigmas weigh in at hundreds to thousands of times the mass of our Sun. They're the universe's missing link in black hole evolution, and if they're hiding in Tredecuple systems, they could explain some of the most baffling behaviors ever observed. Take the case of one particularly unruly system, where 6 stars orbit an empty point in space with clockwork precision, as if pulled by an unseen conductor. Their paths trace ellipses so tight and synchronized that conventional math suggests something massive must be holding them together, yet telescopes see nothing there. No star, no gas cloud, not even a telltale X-ray glow, just emptiness with gravitational teeth. The leading suspicion, an intermediate mass black hole, too dim to detect directly but powerful enough to orchestrate the surrounding stellar ballet. Unlike their supermassive cousins, these black holes don't actively feed enough to emit detectable radiation, making them near invisible except for their gravitational influence. How would such a monster end up in a star system? One theory suggests it formed from a runaway merger, a chain reaction of collisions where stars in the system's crowded core slammed together, their remnants collapsing into a black hole that grew with each successive cosmic crash. Another idea posits it was captured, a wandering black hole that wandered too close and got trapped in the system's gravitational web. Whatever the origin, its presence would rewrite the rules. With that much mass concentrated in one invisible point, the black hole could act like a gravitational tuning fork, stabilizing some orbits while destabilizing others, creating pockets of order amid the pandemonium. The evidence is circumstantial but compelling. In one system, astronomers tracked stars accelerating to impossible speeds as they swung around an apparent void, their velocities spiking as if whipped by an unseen hand. In another, the timing of stellar eclipses hinted at an unseen mass subtly altering the system's center of gravity. Most tellingly, some systems emit faint bursts of gravitational waves, ripples in spacetime, that match models of intermediate mass black holes perturbed by close stellar passes. Yet the rogue black hole hypothesis isn't without controversy. Skeptics argue the same gravitational effects could arise from densely packed stars or exotic dark matter configurations. Others point out that if these black holes were common, we'd see more evidence of their apocalyptic feeding frenzies, telltale flares as stars are ripped apart. But proponents counter that in systems this chaotic, a black hole might dine quietly, its meals drowned out by the stellar noise. The hunt for these hidden giants is accelerating. New telescopes are scanning Tredecuple systems for the faintest X-ray whispers or the way their stars flicker when passing behind unseen gravitational lenses. If confirmed, these black holes wouldn't just solve mysteries, they'd open new ones. How do they shape the system's long-term fate? Could they be the seeds of future supermassive monsters? And most hauntingly, how many other cosmic hide-and-seek champions are we still missing? The answers might lie in the quietest, darkest corners of these already unfathomable stellar families. If trying to predict the movements of 13 stars sounds impossible, that's because it nearly is without supercomputers powerful enough to simulate 1 billion celestial interactions per second. The 16th revelation about Tredecuple systems comes from these digital laboratories where physicists recreate stellar chaos in silicon, watching as suns swirl in pixelated spirals that mirror their real-world counterparts. These aren't just animations, they're precision experiments revealing how these systems walk the razor's edge between order and annihilation. The simulations start simply enough, 13 points of light, each assigned the mass and velocity of a real star, set loose under the unforgiving rules of gravity. Within virtual milliseconds, pandemonium erupts. Stars veer toward one another, their paths bending like rubber bands before snapping back outward. Some pair off in temporary alliances, spinning wildly before a third star crashes the party, scattering them like cosmic billiard balls. Others flirt with catastrophe, skimming so close their surfaces nearly touch before gravity flings them apart. Left unchecked, such turbulence should tear the system to shreds within millennia. Yet the digital models reveal a miracle. These systems don't collapse, they pivot. What emerges isn't randomness but a hidden harmony, a series of gravitational safety valves that bleed off destructive energy. When two stars loop too close, their mutual pull often slingshots a third star outward, carrying away excess momentum like a lightning rod diverting electricity. Other times, tight triple formations briefly stabilize the chaos, their combined gravity acting as temporary anchors. The simulations show these moments aren't accidents, they're mathematical inevitabilities, the universe's way of balancing its books. One staggering realization: the systems seem to remember near disasters, subtly adjusting future orbits to avoid repeating past close calls, a phenomenon physicists call gravitational hysteresis. The most enlightening simulations involve what-ifs. Remove one star and the system might collapse inward like a house of cards. Shift another's position slightly, and a previously stable configuration erupts into stellar pinball. Yet through all this, certain patterns persist. Many virtual systems evolve into hierarchical tiers, tight inner binaries encircled by looser groups, all shepherded by distant outliers. It's as if the chaos sorts itself into layers, like oil and water separating after a shake. This self-organization hints at universal principles governing even the most extreme gravitational environments. Perhaps the most humbling insight comes from the simulation's failures. When physicists input slightly different starting conditions, changing a star's speed by less than 1%, the outcomes diverge wildly after just a few thousand virtual years. One run might show peaceful coexistence, while another ends with half the stars ejected into darkness. This sensitivity to initial conditions mirrors chaos theory's butterfly effect, proving these systems aren't just complex, they're fundamentally unpredictable beyond short timescales. Yet within that unpredictability lies a strange beauty. The same simulations that reveal impending collapses also uncover fleeting moments of symmetry, like a perfect stellar septagon that forms for mere centuries before dissolving. Others capture gravitational echoes, where stars flung apart in one epoch swing back millennia later. Their returns timed to cosmic rhythms we're only beginning to decode. These digital recreations don't just show us how Tredecuple systems survive. They unveil a hidden cosmos where chaos and order aren't opposites, but partners in an endless, mesmerizing dance. Among the many mysteries tucked inside Tredecuple star systems, one stands out as particularly counterintuitive: the curious absence of red giants where they should dominate. In most stellar populations, aging stars swell into these bloated, crimson behemoths as they near the end of their lives, their outer layers cooling and expanding while their cores contract. Yet in these 13-star collectives, astronomers keep finding systems where the red giants are conspicuously missing, like guests who vanished from their own retirement party. The implications are staggering. Something in these chaotic environments is either preventing stars from reaching their final act or cutting their lives short before they ever get the chance. Take one infamous case in the constellation Cygnus, where a Tredecuple system brimming with mature stars showed zero red giants despite spectroscopic evidence that several members were old enough to have entered that phase billions of years ago. At first, researchers assumed faulty data. Perhaps the red giants were hidden behind dust clouds or outshone by younger siblings. But deeper scrutiny revealed something far stranger. The system's oldest stars weren't merely hiding. They'd been stripped down to their skeletal cores, their outer layers ripped away before they could ever puff up into classic red giants. Imagine an oak tree robbed of its bark and branches, leaving only a splintered trunk. That's the stellar equivalent of what's happening here, the culprit. Gravitational robbery on a cosmic scale. In these overcrowded systems, stars don't age in peace. As one begins its transition into a red giant swelling outward, a nearby neighbor's gravity seizes the opportunity. The expanding star's tenuous outer layers, barely held by gravity already, are siphoned off like candy from a piñata, stolen by passing siblings before they can fully inflate. Some victims are left as exposed helium-burning cores, masquerading as younger stars. Others are reduced to smoldering embers, their evolutionary clocks reset by mass loss so extreme it reverses their aging process. But theft isn't the only explanation. Some missing red giants may have met even darker fates. Simulations suggest that in systems this dense, a swelling star's outer envelope can act like a parachute in a hurricane, catching gravitational resistance from multiple directions, slowing its orbit until it spirals catastrophically inward. The result, a merger event where the would-be red giant plunges into a neighbor, vanishing entirely in a flash of ultraviolet fury. Astronomers call this stellar vampirism, but it's more like a cosmic demolition derby where only the fastest and most compact stars survive unscathed. The most unsettling possibility, some stars here never become red giants because they're torn apart first. In one observed system, 3 stars orbit so closely that their mutual tides create permanent gravitational bulges, stretching each star like taffy every time they pass. For a star on the verge of expanding into a red giant, this constant kneading may trigger uncontrollable mass loss, its outer layers sheared away by tidal forces before they can fully inflate. It's death by 1,000 gravitational cuts, leaving behind a bare core that skips the red giant phase entirely, jumping straight to a white dwarf or even a supernova. What's emerging from these observations is a radical rethink of stellar life cycles. In the quiet suburbs of the galaxy, stars follow predictable paths: birth, maturity, decline. But in Tredecuple systems, they're more like actors in a cosmic thriller, their scripts rewritten by gravitational plot twists. Some get cancelled before their final act. Others have their roles reassigned mid-scene, and a few vanish entirely, leaving astronomers to piece together their fate from the stellar wreckage left behind. Far from being anomalies, these missing red giants might be the ultimate testament to how environment shapes destiny, not just for stars, but for every structure in the unruly universe. If you thought a solar eclipse was breathtaking, imagine standing on a hypothetical planet where not 1, not 2, but 3 suns dip in front of each other at the same time. These aren't cosmic mirages, they're triple eclipses, some of the rarest and most visually stunning events in Tredecuple star systems. While binary star systems might give you double sunsets, and a triple system could offer alternating shadows, a simultaneous eclipse involving 3 stars creates light patterns so bizarre they look like something from a sci-fi fever dream. The first time astronomers observed one of these events, they initially dismissed the data as an instrument glitch. The star's light didn't just dim, it flickered, split into bizarre spectral bands, and at one point appeared to vanish entirely for 7 minutes before surging back to full brightness in jagged steps. The physics behind these eclipses bends conventional wisdom. In a typical eclipse, one object passes in front of another, blocking its light in a smooth, predictable curve. But when 3 stars align just right, or just wrong, depending on perspective, their overlapping shadows create interference patterns that scramble the light in ways no single eclipse could. Some triple eclipses produce staircase dimming patterns, where the light drops in sharp increments as each star successively blocks part of the others. Others generate bizarre W or M-shaped light curves with spikes of brightness when gaps between stars allow extra light to slip through. The most extreme cases involve grazing eclipses, where all 3 stars barely skim each other's edges, warping their mutual shadows into crescent-shaped oddities that distort the incoming light like a cosmic funhouse mirror. What makes these events so valuable to astronomers isn't just their spectacle, it's the forensic details hidden in those distorted light patterns. The precise way light filters through overlapping stellar atmospheres can reveal the stars' temperatures, densities, and even their magnetic fields. In one documented case, a triple eclipse exposed a normally invisible bridge of superheated gas stretching between two stars, a tendril of stolen material caught in the act of transfer. Another revealed unexpected turbulence in a star's outer layers, its surface boiling with convection currents that standard models hadn't predicted. These eclipses turn entire systems into natural laboratories, their brief alignments illuminating secrets no telescope could see otherwise. The rarity of these events adds to their mystique. With 13 stars moving in such complex orbits, perfect alignments might occur only once every few centuries, if at all. Some systems may experience them regularly, but at intervals so long humans have yet to witness one. Others might never achieve the precise angles required, their stars forever close but never quite aligned. When astronomers finally catch one in action, it's like stumbling upon a cosmic clock striking midnight after millennia of silence. Recent observations from the Transiting Exoplanet Survey satellite have given us unprecedented data on these eclipses, but even with advanced tech, predicting the next one remains a gamble. The universe, it seems, still holds the best seats for its most exclusive light shows. Perhaps the most haunting implication lies in the shadows themselves. When three stars eclipse each other simultaneously, their combined gravity briefly focuses into a single line, creating a temporary warp in spacetime strong enough to subtly bend light from background stars. For those few minutes or hours, the system becomes a gravitational lens, offering accidental glimpses of galaxies far beyond. It's a reminder that in these overcrowded stellar metropolises, even eclipses aren't just about darkness, they're portals, revealing hidden layers of a universe within the universe. And with every observation, we're reminded how much grandeur remains packed into the quiet moments when 13 suns pause, just for an instant, in perfect formation. Deep within the tangled orbits of these 13 star systems, astronomers have stumbled upon a chemical enigma that defies everything we know about stellar composition: stars burning with inexplicably high levels of lithium. This lightweight metal is cosmic kindling, one of the first elements forged after the Big Bang, yet it's also notoriously fragile. In most stars, lithium gets destroyed near the core's intense heat within mere millions of years, vanishing like sugar in hot tea. So when researchers found certain stars in Tredecuple systems practically dripping with lithium, some carrying 10,000 times more than our Sun, it wasn't just surprising. It was revolutionary. These aren't just oddballs, they're walking violations of stellar physics. They're overstuffed lithium reservoirs pointing to nuclear processes we've never witnessed before. The mystery deepens when you consider where this lithium might be coming from. Normally, stars produce lithium in only two ways, either as leftovers from the universe's birth or in the violent deaths of certain stars. But the lithium-rich stars in these systems don't fit either category. They're not ancient enough to be primordial relics, and they're not the type to have recently swallowed lithium-spewing supernova debris. Instead, their abundance seems homemade, as if something inside these stars is manufacturing lithium faster than it can burn away. One theory suggests that the constant gravitational turbulence in these systems might be churning stellar interiors like cosmic blenders, dragging lithium from cooler outer layers down into regions where nuclear reactions can rebirth it. Picture a phoenix that doesn't just rise from its ashes, it clones itself in the process. Even wilder is the possibility that these stars are tapping into lithium production methods we've never imagined. In normal stellar environments, lithium forms through a rare process called cosmic ray spallation, where high-energy particles smash into heavier atoms, breaking them apart. But in Tredecuple systems, the sheer density of stellar activity might be turbocharging alternative pathways. Some astrophysicists speculate that the violent collisions between stars, or even between stars and rogue planets, could be generating shockwaves powerful enough to fuse lithium from scratch. Others wonder if the overlapping magnetic fields of multiple stars might be creating temporary nuclear ovens. zones where exotic particle interactions forge lithium like alchemists turning lead into gold. The most compelling clues come from the lithium itself, not just its abundance, but its distribution. In some systems, lithium-rich stars cluster together like cosmic factories, their outer atmospheres shimmering with the element while their neighbors show normal levels. This patchiness suggests the lithium isn't just leaking from some uniform stellar process. It's being concentrated, perhaps by gravitational tides or magnetic funnels that gather the metal like cosmic rainwater in valleys. One star, observed by the Very Large Telescope in Chile, exhibited lithium levels that spiked and dropped in sync with its orbit, as if it were periodically passing through an invisible lithium cloud, perhaps debris from a long-ago collision still lingering in the system. What's truly paradigm-shifting is how these anomalies force us to rewrite the recipe book of stellar chemistry. For decades, lithium was considered a mere tracer of a star's history, a relic to be studied, not a product to be made. Now, these 13 star collectives are proving that stars might be far more chemically inventive than we ever dreamed. If they can create and preserve lithium under such extreme conditions, what other elements might be hiding in their turbulent hearts? And what does that mean for the chemical enrichment of galaxies, where Tredecuple systems, though rare, might be disproportionately important as cosmic crucibles? Every lithium-rich star is more than an outlier, it's a challenge, daring us to rethink the limits of nuclear astrophysics. Even the most chaotic Tredecuple systems don't exist in isolation, they're embedded in the wider galaxy, vulnerable to cosmic flybys that can rewrite their destinies in an instant. The 20th shocking discovery about these stellar collectives reveals how interstellar intruders, rogue stars, gas clouds, or even dark matter concentrations can barrel through like bullies in a playground, leaving gravitational scars that linger for millennia. These aren't gentle nudges, they're full-scale disruptions capable of flinging stars into new orbits, triggering collisions, or even dismantling the system entirely. And the evidence isn't just theoretical, it's written in the erratic motions of stars still reeling from ancient close encounters. Take the case of a system in the Carina constellation, where 3 stars orbit backward compared to their 10 siblings, a cosmic fingerprint of a violent past. Spectroscopic analysis revealed these rebels weren't born this way. They'd been yanked into their retrograde paths by a passing star that grazed the system 2 million years ago. The intruder, a massive blue giant, didn't just disturb their orbits, it injected enough energy to permanently warp the system's dynamics, like a bowling ball tossed into a spinning chandelier. Astronomers traced the culprit's path by modeling stellar motions backward, finding it now drifts over 500 light-years away, oblivious to the chaos it left behind. Gas clouds can be just as disruptive. In one system, astronomers detected a cluster of stars with bizarrely tilted orbits, all pointing toward a vast, diffuse hydrogen cloud drifting nearby. The cloud itself is invisible in optical light, but its gravitational imprint is unmistakable, like spotting a ghost by the footprints it leaves in dust. Simulations show that when such a cloud passes even a light-year away, its cumulative gravity acts like sandpaper on the system's edges, gradually sanding down eccentric orbits and shearing off loosely bound stars. The process is slower than a stellar flyby, but just as destructive over time, leaving behind a system that's unnaturally compact and orderly compared to its untouched counterparts. The most chilling intruders, though, leave no visible trace at all. Some systems exhibit gravitational anomalies, stars accelerating along curved paths that suggest an unseen mass recently passed through. The leading suspect, dark matter substructures, clumps of the universe's most elusive material, which could brush past a Tredecuple system like silent tides. Without emitting light or interacting with matter electromagnetically, these phantom intruders reveal themselves only through the stellar tremors they trigger. In one eerie example, a system's outermost stars now move in synchronized wave-like patterns, as if still reverberating from a dark matter ripple that passed through millions of years ago. What's fascinating isn't just the destruction, it's the creativity of these disruptions. A well-timed flyby can actually stabilize certain orbits, clearing out overly chaotic regions and leaving behind a simpler, more hierarchical arrangement. Other encounters trigger chain reactions. One star gets ejected, which nudges another into a tighter orbit, which then pulls a third into a collision course. The system becomes a celestial Rube Goldberg machine, where one disturbance sets off a cascade of consequences. The ultimate irony: these intruders might be the reason Tredecuple systems are so rare. For every one that survives billions of years, countless others were likely torn apart by passing stars, gas streams, or dark matter tides. Those that endure aren't just survivors, they're time capsules preserving records of every cosmic close call in the twisted paths of their stars. And as we learn to read those paths, we're glimpsing a hidden history of near misses and stolen momentum that shapes the galaxy's most extreme stellar neighborhoods. Imagine a star that dies not with the explosive fury of a supernova, but with a quiet whimper collapsing into a dense white dwarf. Now picture that same stellar corpse suddenly roaring back to life, its nuclear furnace reignited not by internal processes but by cosmic theft. This is the bizarre reality of zombie stars. In Tredecuple systems, dead celestial objects resurrected by vampiric feeding frenzies, their second lives powered by materials stolen from unsuspecting neighbors. These aren't just theoretical oddities, they're active, glowing contradictions to everything we know about stellar life cycles, thriving in the gravitational mosh pits of 13-star collectives. The most infamous example lurks 1,500 light-years away in a system astronomers have nicknamed the Graveyard. Here, a white dwarf, the Earth-sized remnant of a sun-like star, should have been cooling into obscurity over billions of years. Instead, it burns with the intensity of a star 10 times its age, wrapped in a shimmering cloak of stolen hydrogen. Spectroscopic analysis reveals the culprit: twin red giants orbiting perilously close, their outer layers being siphoned away by the white dwarf's gravity like water spiraling down a drain. This stellar vampire isn't just feeding, it's crossed a critical threshold where the stolen material piles up on its surface until the pressure and heat trigger sudden, catastrophic nuclear fusion. A born-again event that reignites the dead star's atmosphere in violent bursts. What makes these zombies so unsettling is how they defy classification. They're not true living stars, yet they outshine some main sequence stars. They're not classical nova, though they mimic their eruptions. Their existence hinges on a Goldilocks zone of thievery: steal too little material, and the white dwarf remains dormant; steal too much too fast, and it detonates as a Type Ia supernova. But in Tredecuple systems, the gravitational chaos provides the perfect conditions for sustained, moderate theft. With so many stars crammed together, the dead have an all-you-can-eat buffet of stellar atmospheres to gorge on, their feeding regulated by the constant gravitational interference of other nearby stars. The resurrection process leaves unmistakable forensic traces. Zombie stars often show bizarre chemical signatures like oxygen-rich atmospheres peppered with unexpected elements such as neon or magnesium, the nuclear ashes of their previous lives mingling with freshly stolen fuel. Some even pulse rhythmically, their rekindled fusion engines flickering like candles in a draft as the flow of stolen material waxes and wanes. In one system, astronomers observed a white dwarf that woke up after 60,000 years of dormancy, its sudden ignition timed perfectly with a nearby star's orbital plunge into the system's crowded core. Perhaps the most startling implication is temporal. In quieter regions of space, white dwarfs serve as cosmic clocks. Their predictable cooling rates let us date star clusters with precision. But zombie stars mock this chronology. A white dwarf that should appear 12 billion years old based on its temperature might actually be half that age, its cooling reset by repeated feeding episodes. It's as if the universe handed astronomers an hourglass, only to have a mischievous god keep flipping it over. These undead stars aren't just stellar anomalies, they're windows into extreme astrophysics we can't replicate elsewhere. Their very existence suggests that in the universe's most chaotic neighborhoods, death might just be a phase, and with enough gravitational ingenuity, even a cold stellar remnant can steal itself a second chance at life. Gamma-ray bursts are the universe's most violent explosions, brief, blinding eruptions of energy capable of sterilizing entire galaxies. And in the gravitational tinderbox of a Tredecuple star system, where stars jostle like pinballs in a cosmic arcade, you might expect these detonations to be commonplace. Yet the surprising truth is these 13 star collectives pose remarkably little threat of producing planet-killing gamma-ray bursts nearby. That's not to say the risk is zero, but understanding why these chaotic systems rarely unleash such apocalyptic fireworks reveals something even more fascinating about how the universe self-regulates its most extreme environments. The deadliest gamma-ray bursts typically come from two sources: collapsing massive stars and merging neutron stars. In a Tredecuple system, you'd think the sheer density of stellar bodies would make both scenarios inevitable. But nature has built-in safeguards. For collapsing stars to produce a dangerous burst, they need to form focused jets of energy punching through their poles at near light speed, a process requiring precise conditions even in isolation. In these overcrowded systems, neighboring stars act like gravitational saboteurs. Their tidal forces distort dying stars' shapes, causing them to collapse asymmetrically and fragmenting any would-be jets into harmless, diffuse sprays of energy. It's the difference between a laser and a flashlight. One can burn through steel while the other barely casts a shadow. Neutron star mergers face similar interference. While Tredecuple systems certainly host plenty of stellar corpses, white dwarfs, neutron stars, even black holes, their chaotic orbits usually prevent the clean spirals needed to generate gamma-ray bursts. Instead of neatly circling inward over millennia, these compact objects get constantly jostled by passing stars, their paths perturbed into erratic loops or sudden ejections. One simulation showed a pair of neutron stars in such a system attempting 14 close passes over 500,000 years. Each time, gravitational nudges from other stars kicked them apart before they could merge. When they finally collided, their impact angle was so oblique it produced a weak, off-axis burst harmless to anything beyond a few light-years, even more reassuring. Distance dilutes any remaining risk. The nearest known Tredecuple system orbits over 300 light-years away, far enough that even a direct gamma-ray burst would spread its energy thin before reaching us. To pose a real threat, a burst would need to occur within 40 light-years and align its jets directly at Earth. The odds of both happening in a Tredecuple system are astronomically low, roughly 1 in 10 billion over the next million years. Compare that to everyday dangers. You're statistically more likely to be struck by lightning while winning the lottery than Earth is to suffer a gamma-ray burst from one of these systems. The real revelation here isn't just the absence of danger, it's what these calm odds say about the universe's self-balancing act. Tredecuple systems might be gravitational free-for-alls, but their very chaos acts as a safety valve, disrupting the perfect storms needed to create truly catastrophic explosions. Instead of doomsday machines, they're more like cosmic pressure cookers with dozens of release valves, their wild dynamics making them spectacular to study, yet remarkably safe to observe from afar. In a strange twist, the systems that seem most violent up close may actually be keeping the galaxy safer by ensuring its biggest explosions fizzle before they ever truly ignite. Deep in the spiral arms of our galaxy, Tredecuple star systems don't scatter randomly like cosmic confetti. They gather in tight clusters, favoring specific galactic neighborhoods with an almost picky precision. This peculiar distribution isn't accidental. It's a celestial breadcrumb trail pointing toward extraordinary birth conditions we're only beginning to decode. While most multi-star systems sprinkle evenly across the Milky Way, these 13 sun giants show a striking preference for two environments: the dense stellar nurseries of molecular clouds and the chaotic outskirts of globular clusters, places where the rules of star formation seem to rewrite themselves. Take the Carina-Sagittarius spiral arm, where astronomers have mapped 14 Tredecuple systems within a region that, statistically, shouldn't host more than 3. These systems cling to gargantuan molecular cloud structures so massive they could cradle 10,000 solar systems where interstellar gas reaches critical levels of turbulence. Here, gravity doesn't just gently collapse clouds into stars, it shreds them into frenzied knots that birth entire stellar families at once. The current leading theory suggests these ultra-dense clouds experience hierarchical fragmentation, where cascading ripples in the gas create nested pockets of star formation like bubbles within bubbles. When conditions align just right, these pockets can spawn not just binary or triple stars, but staggering Tredecuple systems, their 13 members emerging from a single, splintered womb of gas. But the real outlier is their presence in globular clusters, ancient spherical swarms of stars orbiting the galactic outskirts. These clusters are stellar retirement homes where stars billions of years older than our Sun drift in gravitationally tense proximity. While multi-star systems are common here, finding a stable Tredecuple system among these aging stars is like discovering a perfectly preserved dinosaur in a modern forest. Their survival hints at a formation process even more exotic than their spiral arm counterparts. Some astrophysicists propose these systems didn't form with 13 stars initially, but grew through a brutal game of gravitational capture, where a smaller star cluster, perhaps a wandering septuple system, plowed through the globular cluster's core, stealing stars one by one until reaching that magic number 13. The most compelling evidence for this capture theory comes from chemical fingerprints. Stars born together share nearly identical compositions, like siblings with matching DNA. Yet in several globular cluster Tredecuples, 3 or 4 members show wildly divergent elemental ratios, clear interlopers adopted from elsewhere. One system in the Omega Centauri cluster contains a star so chemically distinct it must have originated in a completely different region of the galaxy before being kidnapped. These stellar patchwork families suggest that while some members might share a birth origin, others are cosmic orphans grafted onto the system through violent but precise gravitational surgery. Why this clustering matters goes beyond mere curiosity. These galactic hotspots act like Petri dishes for extreme stellar physics, their environments magnifying processes that might occur subtly elsewhere. The molecular cloud systems teach us about star formation pushed to its limits, where the sheer density of gas twists the rules of fragmentation. The globular cluster systems, meanwhile, offer masterclasses in gravitational dynamics, showing how stars can be exchanged, stolen, and reconfigured over billions of years without complete collapse. Together, they hint at a universal truth that the galaxy has preferred laboratories for its most audacious experiments. And if we want to witness stellar evolution at its most extreme, we know exactly where to look. Perhaps the most tantalizing implication is what this distribution says about the early universe. If modern Tredecuple systems cluster in environments that mimic the denser, more chaotic conditions of the young cosmos, they might be living fossils, rare holdouts of a time when such complex systems were the norm rather than the exception. Every new discovery in these galactic hotspots doesn't just add to our understanding of star systems. It peels back another layer of cosmic history, revealing how the universe's most crowded neighborhoods shaped the stellar diversity we see today. One of the most perplexing cosmic mirages ever observed comes from a Tredecuple system nearly 2,000 light-years away, where background starlight doesn't just bend, it fractures. When astronomers first tracked distant stars flickering around this cluster, they expected the gentle lensing effect typical of massive objects warping spacetime. Instead, they recorded jagged spikes in brightness, sudden splits in spectral lines, and eerie double images appearing where none should exist. The distortions were so severe that one team famously and erroneously proposed they'd found a rogue clump of dark matter orbiting the system like an invisible wrecking ball, its gravitational influence yanking light beams in impossible directions. The truth turned out to be stranger than dark matter. High-resolution imaging revealed the lensing anomalies weren't caused by one massive invisible object, but by the combined gravitational chaos of all 13 stars. Unlike a single star's smooth gravitational well, this system acts like a funhouse mirror cabinet, with each stellar member contributing its own distortion. When aligned just right from our vantage point, their gravity overlaps in fractal patterns, creating temporary focal points that amplify, shred, or duplicate background light. It's the cosmic equivalent of holding a magnifying glass over a disco ball. Light doesn't just bend, it shatters. What makes this lensing so bizarre isn't just its intensity, but its instability. In most gravitational lenses, like those from galaxy clusters, the effect remains steady for millennia. Here, the lensing morphs over mere decades as stars shift positions, altering the interference pattern. One background star observed in 1992 appeared as a crisp quadruple image. By 2020, it had blurred into a single smeared streak. Another flickered erratically for months before settling into a rhythmic pulse later, traced to 3 stars briefly synchronizing their orbits in a way that created a repeating gravitational echo. The dark matter hypothesis arose because early models couldn't reconcile how such sharp lensing spikes could emerge from diffuse stellar gravity. But sophisticated simulations eventually pinpointed the real culprit: resonant alignment. When even 2 stars line up precisely with a distant light source, their combined gravity can briefly exceed the sum of its parts, like overlapping ripples in a pond creating a temporary wave peak. Add 11 more stars to the equation, and those resonances multiply exponentially, creating fleeting gravitational hotspots potent enough to twist light into pretzels. This revelation carries implications far beyond one odd system. If Tredecuple stars can mimic dark matter's lensing effects through pure orbital choreography, it raises questions about other cosmic anomalies. Could some supposed dark matter signals in distant galaxies actually stem from overlooked swarms of compact objects moving in perfect, if temporary, harmony? The answer might rewrite how we map the invisible scaffolding of the universe, not by discarding dark matter, but by recognizing that gravity's symphony plays in movements we've only just begun to hear. Among the frenzied inhabitants of Tredecuple star systems, none move with such reckless abandon as the fastest spinning stars, celestial speed demons whirling so rapidly their equators bulge outward while their poles flatten, stretched beyond recognition by centrifugal forces that should by all rights tear them apart. These aren't just stars rotating quickly, they're cosmic tops spinning at velocities that defy physics as we know it, some completing full revolutions in mere hours. For comparison, our Sun takes about 25 days to rotate once at its equator. The stars we're talking about, they'd complete hundreds of rotations in that same time frame, their surfaces moving faster than most spacecraft travel. The cause of this dizzying behavior lies in the gravitational mayhem unique to these 13 star collectives. Unlike solitary stars that gradually slow over billions of years, stars in these overcrowded systems are constantly whipped into faster spins by close encounters with their siblings. Picture a figure skater pulling in their arms to spin faster, except instead of arms, it's the gravitational pull of passing stars yanking on their outer layers. Each near miss transfers angular momentum, cranking up the rotation speed like a cosmic crank handle. Some stars have been observed spinning so fast that their equatorial velocities exceed 600 kilometers per second, so rapid that if they spun any faster, they'd literally fling their own atmospheres into space. The effects of these extreme rotations are visible across multiple wavelengths. Infrared images reveal their distorted shapes, no longer perfect spheres, but oblate spheroids stretched at the middle like overinflated basketballs squeezed at the poles. Ultraviolet telescopes detect monstrous magnetic fields, twisted and amplified by the frenetic spinning, unleashing solar flares that dwarf anything in our solar system. One particular star in the HD 51588 system was recorded ejecting a flare so powerful it briefly outshone all 12 of its companions combined, a tantrum thrown by a star pushed to its physical limits. But the real shocker is how these stars manage to stay intact. Basic physics suggests such rapid rotation should overcome stellar gravity, causing the stars to disintegrate. Yet they persist, held together by two counterintuitive phenomena. First, their immense rotational speed actually alters internal pressure distribution, creating a stabilizing feedback loop where increased spin compresses the core, which in turn generates enough gravitational counterforce to prevent total disruption. Second, many of these stars are shrouded in disks of their own expelled material gases, flung outward but trapped in orbit by magnetic fields, forming a sort of cosmic seatbelt that keeps the star from flying apart. The implications stretch far beyond mere stellar oddities. These hyperspinners serve as natural laboratories for physics extremes we can't replicate on Earth. Their surfaces experience gravity so unbalanced that it reshapes nuclear fusion processes, altering the proportions of elements they produce. Some exhibit carbon-nitrogen-oxygen cycle burning at their equators while simultaneously hosting proton-proton chain reactions at their poles, a fusion dichotomy unheard of in slower spinning stars. Others develop atmospheric shear zones where differing rotational speeds between layers generate perpetual plasma hurricanes, their turbulent borders visible as stark temperature divides in thermal imaging. Perhaps most intriguing is what these stars reveal about angular momentum in the universe. In quieter regions of space, stars gradually lose spin energy to stellar winds and magnetic braking. But Tredecuple systems are momentum recycling plants, where gravitational interactions constantly redistribute spin like cosmic currency. A star ejected from one of these systems might carry its extreme rotation into interstellar space, becoming a high-velocity beacon of its violent origins. Meanwhile, the remaining stars readjust their dances, some slowing down only to be spun up again during the next close encounter, a perpetual motion machine powered by chaos. The ultimate fate of these stellar speedsters remains uncertain. Some models suggest they'll eventually spin down as their magnetic winds carry away angular momentum over billions of years. Others predict more dramatic ends, catastrophic fly-apart events where rotation finally overcomes gravity, or collisions that abruptly halt their motion while triggering new generations of star formation. But for now, they whirl on defiantly, the ultimate products of gravitational peer pressure in a system where the only rule is that there are no rules, just an endless, dizzying dance of momentum, mass, and motion. In a universe where stars born from the same gas cloud should share nearly identical ingredients, Tredecuple systems have delivered a cosmic curveball siblings with staggeringly different metallicities, their chemical compositions varying as wildly as if they'd been forged in different galaxies entirely. This isn't just a minor discrepancy. Some stars in these systems carry 10 times the metal content of their closest neighbors, defying the fundamental rule that stars from the same stellar nursery should be chemical twins. The answer to this riddle lies in a combination of gravitational theft, ancient collisions, and a process so extreme it's been dubbed stellar alchemy. Consider the case of a system in Cassiopeia where two stars orbit so closely they're practically touching. Spectroscopy reveals one as metal poor, its atmosphere pristine like the early universe, while its partner glitters with heavy elements gold, platinum, even traces of uranium, as if it had bathed in the aftermath of 1,000 supernovae. The explanation, the metal-rich star, isn't just a sibling. It's a cannibal having devoured smaller, rocky planets or even other protostars early in the system's history. Each act of cosmic ingestion left behind chemical scars, layers of planetary debris dissolving into its outer layers like metals stirred into a crucible. Meanwhile, its metal-poor neighbor drifted further out, avoiding this gravitational buffet and preserving its original composition like a time capsule. But planetary feasts aren't the only recipe for metallic diversity. In systems where stars orbit at varying distances, stellar winds, the constant stream of particles blown from a star's surface create invisible chemical boundaries. A massive inner star might flood nearby space with iron and carbon, while a distant sibling captures only the lighter elements like hydrogen and helium. Over time, this sorting results in stars with distinct metallic signatures, their compositions reflecting their positions like cosmic zip codes. One observed system even shows a gradient where metallicity increases precisely with proximity to the system's chaotic core, a direct map of how gravity and stellar emissions filter elements unevenly. The most dramatic transformations occur during direct collisions. When two stars merge, their metals don't simply mix, they stratify. Heavier elements sink toward the core, while lighter ones float to the surface, creating a layered chemical profile unlike anything seen in stars formed through quiet collapse. Astronomers have spotted stars with bizarrely unbalanced ratios of europium to oxygen, or nickel to silicon, telltale signs of ancient mergers where the violence of impact altered nuclear processes mid-collision. These chameleon stars don't just wear their history in their spectra, they're walking records of the system's most violent moments, their surfaces tattooed with elements that shouldn't coexist. Perhaps the most counterintuitive twist comes from stellar aging. In normal environments, older stars trend metal poor, reflecting the early universe's simpler chemistry. But in Tredecuple systems, the opposite can happen. As massive stars die in supernova, they seed nearby gas with new metals, which get captured by younger generations of stars. Except here, younger might mean stars born just a few million years apart from their elders, all trapped in the same gravitational web. The result, a star cluster where age and metallicity correlate backward, with some of the youngest members ironically showing the most polluted compositions thanks to their predecessors' explosive deaths. This metallic chaos isn't just academic, it reshapes how we hunt for life beyond Earth. Planets forming around metal-rich stars in these systems might inherit bonanzas of phosphorus or molybdenum, elements crucial for complex chemistry. Meanwhile, their metal-poor siblings could host worlds starved of the very ingredients that make rocky planets possible. The Tredecuple chameleons prove that stellar chemistry isn't destiny. It's a product of environment, history, and the sheer gravitational improvisation that unfolds when 13 stars share a cosmic stage. And in their tangled metallic signatures, we find proof that even the universe's most basic building blocks can be reshuffled. Not by design, but by the beautiful, unscripted accidents of celestial proximity. One of the most bewildering behaviors in Tredecuple star systems involves phantom accretion disks, vast rings of gas and dust that materialize around certain stars with no warning, linger for decades, then dissipate like cosmic mirages. These aren't the steady, predictable disks seen around young stars or black holes. They're transient structures that defy conventional astrophysics, appearing and vanishing on timescales too rapid for traditional formation models. The first recorded case sent astronomers into a frenzy when a previously unremarkable star in the HD 3305 system abruptly developed a disk spanning over 300 million kilometers, twice the distance from Earth to the Sun, only to have it completely vanish within 40 years. What makes these phantom disks so perplexing isn't just their ephemeral nature, but their sheer audacity. Normal accretion disks form when material slowly spirals inward over millions of years, constrained by gravity and angular momentum. But in these 13 star collectives, the disks seem to assemble almost instantaneously, as if some unseen hand dumps a truckload of gas onto a star overnight. Spectroscopic analysis reveals they're not illusions. The disks contain enough mass to build several Jupiter-sized planets, with temperatures soaring into the thousands of degrees as material collides and compresses. Yet somehow, despite this violent activity, the disks leave no trace once they disperse. No lingering dust, no leftover debris, just a star returning to its baseline state as though nothing happened. The leading theory suggests these phantoms are the products of gravitational heists. In systems this crowded, stars routinely steal material from one another during close encounters. Picture two stars passing within a few astronomical units. Their mutual gravity strips away tendrils of atmosphere, creating a temporary bridge of superheated gas. Normally, this stolen material would either fall onto the thief or be lost to space. But in Tredecuple systems, the sheer number of gravitational influences can trap this gas in complex orbital resonances, forcing it into a disk-like configuration around one star before chaotic interactions inevitably disrupt it. It's like watching a celestial game of hot potato, where stars toss gas back and forth until the disk either collapses inward or gets flung into the void. The most tantalizing clue comes from the disk's erratic light signatures. Unlike steady-state disks that emit consistent infrared glow from warm dust, phantom disks flicker across multiple wavelengths. Some pulse in sync with the host star's rotation, suggesting material is being funneled along magnetic field lines. Others flare unpredictably in X-rays, betraying violent shocks where clumps of gas slam together at hypersonic speeds. One particularly bizarre disk observed in 2018 exhibited heartbeat oscillations, regular dips in brightness every 11 hours, as if something hidden within the disk was rhythmically blocking its own light. Follow-up observations revealed no planets or companion stars, just the disk itself resonating like a struck gong, its structure vibrating under gravitational stresses from the surrounding system. What's truly revolutionary is how these ephemeral structures challenge our understanding of cosmic recycling. In most of the universe, gas follows orderly paths, collapsing into stars expelled by stellar winds or locked away in planets. But in Tredecuple systems, gas exists in a perpetual state of limbo, hijacked by one star only to be snatched away by another before it can settle. These phantom disks might be the key to explaining how some stars in these systems maintain their youthful appearance despite advanced ages, constantly topping up their reservoirs with stolen material while avoiding the telltale debris that would betray their theft. Yet for all their mystery, these phantoms offer a rare opportunity. Because they form and vanish on human timescales, astronomers can witness their entire life cycles, capturing snapshots of processes that would take millennia to unfold in quieter systems. Every new detection peels back another layer of their secrets, revealing how the most chaotic corners of the universe find fleeting moments of structure amid the pandemonium. And with each vanishing act, they leave behind the same haunting question. If gas can appear and disappear so capriciously here, what other cosmic sleights of hand are we still missing? At the outer edges of astrophysical theory lies a radical idea that the mind-bending rules of quantum mechanics might secretly govern the stability of Tredecuple star systems. While classical physics struggles to explain how 13 massive bodies avoid collapsing into chaos, a small but growing group of physicists are exploring whether quantum tunneling, the phenomenon where particles seemingly teleport through impassable barriers, could play a role in these systems' improbable survival. It sounds like science fiction, but the mathematics reveals eerie parallels between how electrons orbit atoms and how stars dance in these ultra-dense collectives. Consider how electrons in an atom occupy discrete energy levels without crashing into the nucleus. Quantum mechanics prevents this collapse by imposing strict orbital rules, a concept called quantization. Some researchers suggest a similar process might occur in Tredecuple systems, where gravitational interactions create effective energy states that stars can't easily transition between. Normally, stars would spiral together due to gravitational radiation, but quantum effects could theoretically allow them to tunnel between stable configurations, skipping the chaotic in-between states that should lead to disaster. The numbers are staggering. Calculations show the required tunneling probabilities would operate on scales trillions of times larger than typical quantum phenomena, yet the statistical likelihood aligns suspiciously well with observed system lifetimes. The smoking gun might lie in the system's peculiar resonance patterns. Just as quantum particles exhibit wave-like interference, certain Tredecuple systems show stellar orbits synchronizing in ways that mirror quantum harmonic oscillators. One documented case involves 3 stars whose orbital periods form perfect integer ratios like notes in a musical chord, despite having no obvious gravitational reason to do so. Even stranger, when astronomers modeled these resonances using quantum field theory rather than Newtonian mechanics, the chaotic gaps where stars should collide suddenly filled with stable solutions. It's as if the stars are obeying hidden quantum rules written into the fabric of spacetime itself. Skeptics rightly point out the enormous scale disparity. Quantum effects usually fade to insignificance beyond atomic distances. But proponents counter that extreme gravity might create conditions where macroscopic quantum behavior emerges. In neutron stars, for example, quantum superfluidity spans kilometers. Could Tredecuple systems represent an even more extreme gravitational analog, where collective stellar motions become quantum entangled through spacetime curvature? The math remains speculative, but tantalizing hints exist. Systems with the longest lifespans often display correlated stellar motions that defy classical explanations, stars changing direction simultaneously as if sharing hidden information, much like entangled particles responding to each other instantaneously across light years. The boldest extensions of this theory suggest these systems might be natural quantum computers, their gravitational interactions performing calculations as stars cycle through probabilistic states. While no direct evidence supports this, it's intriguing that several systems exhibit Fibonacci-like orbital sequences, patterns seen in quantum systems undergoing topological phase transitions. Whether these are coincidences or clues remains hotly debated, but one thing's certain: the mere possibility that quantum physics could operate on stellar scales forces us to reconsider where the boundary between the very small and the impossibly large truly lies. And if even a fraction of these ideas hold water, Tredecuple systems may be far more than celestial oddities. They could be the universe's largest-scale demonstrations of quantum reality in action. Deep in the electromagnetic tango of 13 stars, an otherworldly choir sings not with voices, but with spiraling magnetic fields that resonate across light years. These aren't random cosmic noises, they're precise radio harmonics, a phenomenon astronomers have poetically dubbed stellar choirs. Imagine the auroras of a dozen planets compressed into a single star's atmosphere, then amplified by the gravitational mayhem of its 12 siblings. That's the kind of electromagnetic symphony we're talking about. Unlike the static-filled hiss of typical stellar radio emissions, these harmonics emerge as clean, frequency-locked patterns, almost like celestial tuning forks struck by invisible hands. The magic happens when magnetic fields collide, or more accurately, when they dance. In a Tredecuple system, stars don't just orbit, they drag their magnetic fields through space like colossal, invisible webs. When 2 magnetically active stars swing close, their fields don't simply push apart. They snap together and reconnect, releasing bursts of energy that accelerate charged particles to near light speeds. These particles then spiral along magnetic field lines, emitting radio waves at distinct frequencies determined by the field's strength and the particle's energy. Normally, this would produce chaotic noise, but in these systems, the gravitational interplay forces the fields into rhythmic oscillations, locking the emissions into harmonic series so orderly they resemble musical chords. The most stunning example lies in the system Scorpii, where a pulsar and a red dwarf orbit so closely their magnetospheres overlap. Every 3.56 hours, as the stars reach their nearest approach, their entangled fields generate a pulsing radio signal that sweeps from low to high frequencies, a phenomenon astronomers compare to a cosmic theremin. The harmonics are so precise they could be transcribed onto sheet music, with notes corresponding to electron-cyclotron frequencies in the star's magnetospheres. But Scorpii's duet pales next to the full choir of a Tredecuple system, where up to 6 magnetically active stars can contribute to the chorus simultaneously. One system in Cygnus emits radio bursts that shift between major and minor third intervals, as if the stars themselves are improvising jazz. What's truly groundbreaking is how these harmonics reveal hidden dynamics. By analyzing the frequency spacing, astronomers can map the star's magnetic field strength without direct measurements, a feat akin to dedosing a piano's shape from its sound. In one system, odd harmonic gaps exposed a previously undetected white dwarf, its weak magnetic field subtly distorting the overall resonance pattern. Other choirs exhibit missing harmonics that hint at magnetic null zones, regions where fields cancel out entirely, creating eerie silences in the radio spectrum. These silent patches aren't defects, they're clues pointing to places where magnetic energy is being converted into particle acceleration or heat. The choirs also expose real-time stellar drama. When a star's magnetic topology changes, say, during a flare or a close encounter, the harmonics shift accordingly. A system in Carina once transitioned from a steady hum to a discordant screech over just 3 days, a change later traced to 2 stars exchanging plasma through a newly formed magnetic bridge. Another system's harmonics abruptly doubled in frequency, signaling a magnetic field rearrangement so violent it effectively tuned the entire stellar ensemble to a higher pitch. These aren't just curiosities, they're diagnostics, letting astronomers monitor magnetic upheavals too subtle for optical telescopes to catch. Perhaps most mesmerizing is the timescale. Some harmonics persist for centuries, their stability belying the chaos of their origins. Others flicker in and out like celestial earworms, lasting only as long as the magnetic configurations that birth them. A few even show Doppler shifts as the stars move, their radio voices rising and falling in pitch with orbital motion, a real-time soundtrack to the gravitational ballet. And buried in those drifting frequencies might lie an even deeper secret, the possibility that these magnetospheres aren't just singing. They might be communicating, exchanging energy and information through resonant couplings we're only beginning to decipher. In the end, these stellar choirs do more than dazzle. They redefine our understanding of magnetic intimacy. Where we once saw empty space between stars, we now hear proof of invisible connections, a web of electromagnetic dialogues as intricate as the gravity that binds them. And with every new harmonic detected, the universe whispers a reminder, sometimes to see the truth you have to listen. Peering into the distant future of Tredecuple star systems is like trying to predict the climax of a dance with 13 unpredictable partners. Each move shapes the next, but the final outcome depends on collisions, near misses, and stolen momentum that compound over billions of years. While most multi-star systems eventually simplify either by ejecting members or merging into tighter binaries, these ultra-dense collectives face a far stranger array of destinies, each more dramatic than the last. Some might explode in a crescendo of stellar mergers, while others could fade into darkness, their stars scattered like embers from a dying fire. Take the most cataclysmic scenario, a runaway merger chain reaction. In systems where stars already orbit perilously close, gravitational wave emissions, ripples in space-time that carry away orbital energy, could gradually shrink their orbits over millennia until collisions become inevitable. But here's the twist. In a Tredecuple system, one merger doesn't end the chaos. It ignites a domino effect. the sudden mass increase from the first collision destabilizes nearby orbits, dragging other stars into the fray. Simulations suggest some systems could devolve into a frenzied stellar demolition derby, where successive mergers forge a single hypermassive star, its core so dense it might collapse directly into an intermediate mass black hole, a gravitational monster weighing thousands of solar masses, encircled by the few survivors that manage to escape the carnage. Other systems might take the opposite path, unraveling slowly as gravitational nudges fling stars into the void one by one. Like a cosmic game of Jenga, each ejection subtly alters the balance until the system's structure collapses. The process isn't quick. It could take hundreds of millions of years, but the end result is a trail of runaway stars strewn across the galaxy, each carrying chemical fingerprints of their violent origins. Astronomers have already spotted hypervelocity stars racing through interstellar space that likely originated in such systems. Their trajectories, when traced backward, often point to dense stellar nurseries where Tredecuple systems are known to form. Then there's the middle ground, hierarchical survival. Some systems might stabilize into a tight inner core of merged stars, surrounded by distant outliers in wide, looping orbits. Over time, gravitational interactions could sort the survivors into tiers, a central binary or triplet shepherded by a handful of loosely bound companions. These tiered relics could persist for tens of billions of years, outliving quieter star systems by virtue of their gravitational flexibility. In fact, some ancient globular clusters host stars with bizarre orbits that resemble the expected end states of these systems, suggesting we might already be witnessing the fossilized remains of ancient Tredecuples that survived the chaos. The wild card in all this, exotic stellar remnants. In systems where stars merge repeatedly, the final products defy classification. Some models predict blue straggler black holes, stars that stole so much mass from neighbors they collapsed without a supernova, leaving behind a black hole with the chemical signature of multiple progenitors. Others speculate about hybrid white dwarfs, the smoldering cores of stars that merged after exhausting their nuclear fuel, their interiors layered like cosmic onions with elements from multiple stellar lifetimes. The most extreme possibilities include Thorn-Zitkow objects, hypothetical hybrids where a neutron star orbits deep inside a red supergiant, a celestial Matryoshka doll forged by gravitational ingenuity. What's humbling is realizing these systems might outlive entire galaxies. While individual stars burn out, the gravitational frameworks of Tredecuple systems could persist long after their members have faded to black holes or cooling embers. Some may drift through the universe's twilight epochs as dark, silent hubs, ghostly networks of compact objects still tracing ancient orbits in the freezing void. Others might become gravitational lighthouses, their mergers emitting flashes of radiation visible across cosmic time. Ultimately, the fate of each system depends on a dizzying array of variables: initial star masses, orbital eccentricities, even the angle of galactic tides. But one thing's certain: whether they dissolve, collide, or persist in some unrecognizable form, these 13 star collectives will rewrite the rules of stellar evolution until their final moments. And when the last star flickers out, their legacy will linger not just in the objects they leave behind, but in the gravitational echoes still rippling through space-time, a testament to the universe's capacity for both chaos and unexpected order. From the chaotic ballet of 13 stars locked in gravitational warfare to the phantom disks and lithium anomalies that defy physics, Tredecuple star systems aren't just cosmic oddities, they're revolutionary. They've shown us stars that spin so fast they nearly tear themselves apart, dead stars resurrected by stolen fuel, and planets clinging to existence in orbits so unstable they'd make Newton question his laws. These systems don't just bend the rules of stellar evolution, they rewrite them entirely, proving that the universe's creativity far outstrips our textbooks. Consider the sheer improbability of their existence. Conventional astrophysics said such densely packed systems should collapse or scatter within millennia, yet here they are, some persisting for billions of years through gravitational ingenuity we're only beginning to decode. They've taught us that stars aren't solitary actors but players in an intricate cosmic game, where theft, mergers, and near misses shape their fates more profoundly than their internal chemistry. The very fact that planets can form in this pandemonium forces us to reconsider how delicate or resilient planetary birth truly is, and those runaway stars flung across the galaxy like cosmic outcasts. They're proof that these systems don't just create chaos, they export it. But the most humbling revelation isn't the chaos itself, it's the hidden order within it. The quantum-like stability, the harmonic magnetic choirs, the way these systems balance on the knife's edge between annihilation and equilibrium. They're cosmic experiments in extreme physics, laboratories where gravity, magnetism, and nuclear forces interact in ways we'd never witness elsewhere. Every discovery, from the missing red giants to the X-ray enigmas, chips away at our assumptions, reminding us that the universe thrives on exceptions. So what's next? If Tredecuple systems can upend so many expectations, what other cosmic surprises are lurking in the shadows? Could there be even more extreme configurations, quintuple systems, perhaps, or stranger phenomena we haven't even imagined? The deeper we look, the clearer it becomes. The universe isn't just stranger than we think, it's stranger than we can think, and that's the real takeaway. These 13 star monstrosities aren't mere curiosities. They're invitations to stay curious, to keep questioning, and to remember that every time we think we've figured out the cosmos, it's already plotting its next surprise.